Here we are again. Now, in the centuries since Newton first stated his laws, we have learned that they are not arbitrary at all, but instead they reflect deeper aspects of nature known as conservation laws. So, in here we'll explore three of the most important conservation laws for astronomy: the conservation of momentum, that is very nicely exemplified by collisions. Then your conservation of angular momentum, which stated here is actually what Kepler's second law is about, even though Kepler had no idea about that. And then the conservation of energy and how, for example, how that applies to the birth of stars and many, many other situations. So we'll see actually some immediate examples of how they apply to astronomy, and then use these laws over and over throughout the rest of this course. So you might have wondered already, why do objects move at constant velocity if there is no force that acts on them? They go hand in hand, right? We were saying, well, if it's constant velocity, then that means there is no acceleration, so there is no force. All right, well, actually, this is very much related to the fact that the momentum, remember that momentum, the linear momentum, P, that's the product between the mass and velocity. Remember that? Okay, so here's an example of collisions of two balls. So you have first ball that's coming with a certain momentum, therefore velocity, bumping into a second ball that was at rest. Okay, here's where the collision happens, and after the collision, the first ball's momentum ends up being 0, so it's going to be at rest, while the second ball actually has all the momentum that was transferred from the ball number 1 now, as it's moving with the same velocity as first ball was moving before the collision. So the thing is, you look at that, when they collide, right, one acts upon the other, but because of Newton's third law, these forces are equal and opposite. So that means no net force, right? These interacting objects, they exchange momentum through equal and opposite forces. Right? Equal and opposite, they cancel one another, so there is no net external force that's acting upon them. No net external force, it's going to be no change overall for this system. Okay, how about the other momentum, the other type of momentum? That was the angular momentum. Does anyone remember what was the formula for that? So angular momentum, that is the product between the mass and velocity and the kind of the arm of the rotation. So the angular momentum is very useful when we characterize things that change direction. Actually, they rotate around something. Okay, so it turns out the conservation of angular momentum explains why objects rotate faster as they shrink in radius. Look at this example, the skater. All right, so extended arms, that means larger radius, while this is happening, right, because this product between the mass and the velocity and the radius actually stays constant when you go to smaller r, that means that translates into larger velocity, right? Because the product m times v times r needs to stay constant. Okay, so the larger the radius here, the smaller the velocity will be, assuming that this will stay constant, like the skater doesn't lose any mass in the process. Okay, now this angular momentum conservation also explains why there are so many spinning disks in the universe. Spinning galaxy, spinning torus, or the kind of dusty torus. It does look like a donut, right? Like a toroid, dusty torus around an accreting black hole. Or this is basically the accretion disk. Around a white dwarf. We'll learn about all these things later on. These are really nice examples. So you see, we're going to meet these laws of conservation fairly often actually from now on. So it was important that you understand what they are and why do they happen. Here's another example. Application of the conservation of angular momentum. So what do we have here? Planet, right? Say it's here. This is the velocity. This would be the radius, right? And then in this case, right, when it's here, here's the velocity. Can you tell, is it, if you remember, is it smaller here or larger? It's faster, right? Faster when closer to the sun. Remember, so velocity here, okay? And then the radius. And it makes a lot of sense, right? So what do we have? This is smaller and this is longer or larger. So what do we have here? Here we have m times v times r, right? Here is also m times v times r, right? But this is small and this is large. While here, this is large and the velocity is smaller, larger, right? It's all by comparison. All right. The thing is that the angular momentum in a point A, okay, is actually the same as the angular momentum in point D. So L in point A is equal with L in point D. And actually you can, by the same line of arguments, it's going to be the momentum, the angular momentum in point B, or the angular momentum in point C, or angular momentum in any point or position of the orbit. Okay, so velocity changes, the radius changes, but it's something that stays constant. Earth experiences no twisting force as it orbits the Earth, the Sun, Earth or Mars or anything else that orbits the Sun. So its rotation and orbit will continue indefinitely. Okay. Now, our third and crucial conservation law for astronomy is the law of conservation of energy. Now, this law tells us that like momentum and angular momentum, linear and angular momentum, the energy cannot appear out of nowhere or disappear into nothingness. Objects can gain or lose energy only by exchanging energy with other objects. And so it's actually because of this law that the story of the universe is a story of the interplay of energy and matter. All actions involve exchanges of energy or the conservation of energy from one form to another. And so, before we actually talk about the conservation of energy, let's review maybe some basic types of energy. Basic, okay? Now, one of them is the kinetic energy, okay? And it says here motion, right? You're probably familiar with this term, right? Motion, kinetic, right? But it's also added here temperature. We're going to talk in a second about it, okay? Why actually temperature is a measure of the average kinetic energy, like how much motion happens inside a certain body for which you measure the temperature. There is also the radiative type of energy, and that is usually related to light, and we're going to have the whole of chapter 5 actually to discuss about the nature of light and how light interacts with matter, the properties of light. So that's not going to be the subject of discussion here. And then there is the potential or stored energy, right? It's like, hey, it's the calories that you're eating, if you want, the food that you're eating, and then you would, right? Instead of that, that could be maybe food, and that's converted into energy, or you actually need energy. You need this food to produce this kinetic energy. You actually need the radiative energy, right, in order to process the food to convert it into the energy that you need to move around. So what I'm saying is here that the energy can change type, but it cannot be destroyed. All right, and very much in line with this is the fact that actually there is no loss of energy, period. The total energy content of the universe was actually determined in the very beginning of the universe, in the Big Bang, and it remains the same today. You're not losing energy. Energy, if you feel that you don't have the energy that you're used to, well, that only means that energy has been converted into a different type. That's all. So I promised you we're going to connect that kinetic energy to the temperature. So some clarification here. So there is thermal energy, and some people relate that or just kind of think of temperature as being energy. Well, thing is, they are totally different things. So now thermal energy, that is the total kinetic energy of all the particles that make up the system, the object for which you're calculating or you want to measure the thermal energy. So it says here the collective kinetic energy of the particles that are in a rock, in the air, in water, or so on, right? Okay, so thermal energy is related to the temperature, but it is not the same, okay? Because the temperature is the average kinetic energy of the particles in a substance. Now, the thermal energy, that depends on the density or number of particles, the total number of particles per, right, unit volume. So you really need to know volume. Okay, you really need to know how many particles are out there, right, to add all their kinetic energies up. for the temperature, you just take the average of the kinetic energy of all the particles that make up a substance. So we have here two examples, right? So this is in average small velocity and therefore small kinetic energy, and that's the formula for the kinetic energy, the mass times velocity squared divided by 2. And here, as you can see, right, longer arrows means higher average speed, right? Therefore, higher kinetic energy. In average and total, right, which is 1/2 mv squared. Pretty interesting, isn't it? Okay, so that is the thermal, right, or kinetic energy. Any other types of energies? We already mentioned. There is the potential energy. And one of the types of potential energy we're going to hear about and talk about, discuss in this class is the gravitational potential energy. On Earth, that gravitational potential energy, that is basically the product of the mass, the strength of the gravity or gravitational acceleration, and the height above the ground, right? So kind of this would be h. So you can see that's another h, smaller, and that would be 0. H is 0 on the ground. So here there is a lot of gravitational potential, right? Here, much less. So where did it go? It was converted, right? So here there is a lot of speed. It was converted to, can you guess? Now there is a lot of speed. Here, kind of V is 0. No speed, pretty much no motion. So no kinetic energy. Here, all that loss of gravitational energy in this point was converted to kinetic energy. And that's going to be all of it converted to kinetic energy. So here on the ground, all energy is kinetic energy. Interesting, isn't it? All right, here's another example. In space, an object or say a gas cloud has a lot more gravitational potential energy. So that would be this situation when it is spread out. Okay, so see this? This would be the H, right? Which is large. While here that H is small. What happened to all that gravitational potential? So here is a lot of potential energy. Here it is converted to kinetic energy. This is why this is a fast rotating thing, cloud. This is very weakly, if you want, rotating cloud. So small kinetic energy. Also, small kinetic energy, kind of cold temperature wise, so low temperature. Okay, fast rotating, hot, high temperature. Interesting, isn't it? and yet there is a different type of energy, and it's very important, and it was discovered by Einstein and is given by this formula, which again, man, is messed up. Let me write it again. E is mc squared. I'm sure you have heard about these words put together like this. E equals mc squared. All right, so basically what Einstein discovered was that for any piece of matter, there is a certain type of potential energy that is stored in it, right? So you have a pebble, a certain mass, that can, in principle, be converted into energy, right? Just a gram, if you want, which is 0.001 kilograms. A tiny, tiny bit of matter, right? Well, if you actually calculate that, that is going to be a lot of joules, which is the unit for energy, any kind of energy. All right, and you're going to have in a homework a few examples about for which you need to calculate the energies, either kinetic or and then compare with the mass energy, right? Remember that c is the speed of light. C is 3 times 10 to the 8 meters per second. You can also calculate the energy, the mass energy of yourself, right? And just find out just how much energy you actually have. If only you could extract and use that energy. It turns out that stars are able to extract energy out of some atoms, and we're going to talk about that very soon, actually, in a few chapters. But we as humans, or I don't know, other beings, we have not yet figured out a way to extract the energy from a pebble, for example. It's a lot of energy out there. It would, just a pebble, right? If you were to calculate this energy, that would, provide electricity for a whole town, if not a city, right? So it's a lot of joules. We just didn't figure out how to extract that, okay? There is a lot of concentrated energy, right? And that can actually spontaneously also turn the energy into particles, right? We do that in particle accelerators for very few tiny portions of an atom, right? So that happens at nuclear scales, all right? Or a very small amount of mass, right? Of uranium, say, okay, can actually release a great deal of energy, right? If this mass would be, this much, even smaller amount of uranium, then you get the nuclear bomb. Okay, yeah, we just need to figure out good ways of using that kind of energy. Of course we did, because we have nuclear plants, so those are good things. So now the question is, can we use all this information about energies together with gravity, obviously, to allow us to better understand the orbits? It turns out that the total orbital energy, the gravitational plus kinetic, stays constant, right? Is conserved as long as there is no external force, net force, acting on our system. And there's actually not much out there that acts on the system of the sun with planets around it. Okay, so in that situation, a planet that is revolving around the sun, remember, when it's closer here, it moves faster. When it's further out, it moves slower. It turns out that, of course, if it moves faster, then there is more kinetic energy, and it's closer, there is less potential energy, right? The potential energy plus kinetic energy, that is the total gravitational or orbital energy, and this stays constant. So if that total energy stays constant, that means if the kinetic energy is larger, then the potential energy will need to be smaller. If the potential energy is larger, then kinetic energy will get smaller. But the total orbital energy stays constant. And as long as that happens, the orbit cannot change. And it says there spontaneously. Well, when are the situations when the orbits are changing? One of them can be the friction or atmospheric drag, right? So this is what happens with the satellites. At some point, they're going to lose energy and they're going to be in lower and lower and lower orbits, eventually falling very likely in the oceans. Another example would be the captured moons by Mars. This is what we think happened with Phobos and Deimos, okay? Must have happened when enough friction caused energy loss for some of the asteroids. Another cause is a gravitational encounter, and here is an example, right? So what do we have? That's a comet, right? That comes on its parabolic or hyperbolic orbit. This was supposed to be the orbit if it were not for the gravitational encounter with Jupiter. Jupiter is pretty massive, so what did it do? It deflected the orbit, right? So it changed the orbital energy of the comet. Comet lost energy, and so the orbit became converted from being parabolic or hyperbolic, that is open orbit, lost energy, and became closed orbit. Ellipse. This is the new orbit after the Jupiter encounter. So yeah, cool examples. And I think that's it for now.